Hello, welcome back. Make sure to watch parts 1 and 2 if you haven't already. The links are in the description for parts 1 and 2. All right, so this time we have a function of two variables, x and y, and a region bounded by 3 curves. This one will be harder to visualize, so it's even more important to draw the input space this time. So, since there are 2 input variables, the input space is 2-dimensional. We'll draw an x-axis and a y-axis, one for each input variable. And I'm actually going to draw this in the pretty much only the first quadrant because I've done this problem before and I kind of know what this looks like. But in general, you want to draw your axes a little more centered, but I'm going to go with the first quadrant because I know what this problem looks like. Let's see. Each boundary is described by a linear equation, so each boundary is a straight line. X equals 2 in particular is a vertical line at, well, x equals 2. So I'll go say 2 tick marks over, something like that. X equals 2 there. It's on the x-axis because it's x equals 2. And then every point along this line has an x-coordinate of 2. That's how I know it's a vertical line. I'm going to label that as well, x equals 2, like that. There we go. That's what that line is. All right, the next one, y equals x minus 2, is in slope-intercept form, mx plus b. The y-intercept is -2, so actually I do end up needing the lower half here a little bit. I'll make this proportional, 1, 2, -2 there. That's the y-intercept. And it's got a slope of just 1, so that means for every 1 I move over, I move up 1 also. So that would be, say, from this point, we go up 1 over 1, up 1 over 1. See a point there, we can continue that trend there. Something like this. Of course, I'm a mathematician, not exactly an artist, so drawing is a little bit imprecise. It's a good idea to make it as precise as possible, but, you know, it doesn't have to be perfect, of course, as long as all the details are roughly correct. And then the last line has a y-intercept of 4, so I have to walk up 4 steps on the y-axis. 1, 2, 3, 4, somewhere up there. And it's got a slope of -1 now, so it looks the same as that line, 45 degrees, but facing down instead of up. So I'm going to go, say, down 1 over 1, down 1 over 1, something like right there, we'll say. Continue that trend in both directions. Something kind of like that. And I have an intersection point over there as well. Yeah, okay, that's that. Yeah, okay. All right. There are a lot of lines here, so it can be a little tricky to tell which region is actually the region that the problem gave us. The problem said that the region is bounded by these 3 lines, the 3 blue lines in this case, so it must be the triangle in between them. So I'll shade that in here. That can be useful to shade in pretty early there. It's tempting to use one of these other regions because I see this kind of cutting, say, a little parallelogram there. I see a triangle over there, a triangle over there. So it's tempting to pick one of those other regions. Just remember the axes themselves, unless they're given in the problem to be the boundaries, they are not the boundaries in this case. It is just those 3 lines. So don't use those as your boundary. Make sure it's the region between those 3. You could also perhaps say maybe this region, but that region's only bound by those 2 lines. Well, I mean, technically it's bounded on all 3 sides there by those 3, but it's not bounded, if you will. So it's bounded by all 3 of those lines. So just make sure we actually have the right region there. That can be a little bit tricky to see there. So now we have a clear picture of the input space. So let's draw the same table as before. Let's say I draw a boundary here. We'll want a geometry column to label where each point came from. We need columns for the inputs, in this case x and y. We only had x before, so x and y. And then we need a column for the output, which is f of x and y. So we'll do something like this. There we go. As before, we'll fill in the geometry column with everything we need to test. The given region is a triangle, which has an interior, 3 edges, and 3 vertices. So we'll say, I don't know, we can say the interior first. Then we have, say, the left edge. Left edge, we could do the upper edge. And the lower edge. And as for the vertices, we've got 3 of them. We've got the upper vertex. We have a lower vertex. And a right vertex, I'll say. Before we automatically knew the locations of the vertices, this time it will be a little trickier. We need to find the intersections of these three lines, which is a relatively simple algebra problem, although we might have to get a bit creative. The upper vertex, oh, I forgot to label my other line. So this one is x equals 2. The upward sloping line is y equals x minus 2. And the downward sloping line is y equals negative x plus 4. It's not absolutely imperative to label those, but it can be really useful because we're about to find the intersections between the lines and we need to reference these. So it's useful if it's directly on the graph instead of having to go back to the problem statement every time. So we'll start with the upper vertex. We want to find the coordinates of that point there. That's the intersection between x equals 2 and y equals negative x plus 4. Well, one of those gives you the x coordinate automatically. So for the left edge, x is 2. I can fill that in automatically. As for the y coordinate, we'll have to find where this intersects with the other line. And we have a relationship between x and y right there. Y equals negative x plus 4. So we can plug in x equals 2 into that line. So I'm going to say y equals negative x, but instead of x, I'll use 2. Plus 4, which altogether makes 4 minus 2 is 2. So at that point, the x coordinate is 2 and the y coordinate is 2, which looks about right from the graph. Again, your drawing doesn't have to be perfect. Mine obviously is not perfect, but it looks close enough there. It looks like it is actually at 2, which is kind of handy. The lower vertex is similar. That's on the left edge once again, so we automatically know that x is 2 over there. And it kind of looks like it goes through 0 there, actually. I'd like to double check that by plugging it into the equation there. This is an intersection of x equals 2 with y equals x minus 2 there. So I'll use that formula, y equals x minus 2. But of course, we know x is 2 in this case. And 2 minus 2 is 0, and that looks like the correct value there. So my lower vertex is at 2, 0. Lastly is the right vertex. This one will be the trickiest one. That's the intersection between y equals x minus 2 and y equals negative x plus 4. We want to treat this as a simultaneous system of two equations and two unknowns. So I'll write those down here. We'll say y equals x minus 2 and y equals negative x plus 4. And I need to find the value for x and the value for y that satisfies both of these equations simultaneously. I think the easiest method for this, since we have y equals and y equals, is just use substitution. If y equals x minus 2, then I can rewrite the second equation, for example, say y, which is x minus 2, equals negative x plus 4, effectively setting these two pieces equal to each other because they're both equal to y. So I can solve for x here. I'll say add x to both sides. You get 2x minus 2 equals 4. Add 2 to both sides, 2x equals 6. And divide by 2, we get x equals 3. And we can put that on the table. That is the x coordinate of the intersection of those two lines there at the right corner, the right vertex. So we'll say x is 3. Of course, we also need y here, so we can plug x equals 3 into either equation. I'm going to do both just so we can confirm that we have the right answer. Let's see, so y equals, say, 3 minus 2, which makes 1. So not too bad. We could try the other one, y equals negative 3 plus 4, which is also 1. You should get the same result there because it's the same intersection point there. Otherwise, if you get different results there, that means you made some kind of mistake in finding x or in finding the y. So we can put this in the table. Y is 1 for x equals 3. There it is. And we have all three of our vertices. Next, we need to test each edge. We'll start with the left edge. There's an entire space of points here, so we need to use derivatives, although we also need to ensure that our result shows up on this boundary. So to do that, we can plug in what we know about this boundary into the function. In this case, that boundary is described by x equals 2. So we can plug in x equals 2 into the function. I have the function right there, f of x, y, and I'm going to plug in x equals 2. So f of x, which is 2, comma, y, we don't know anything about y at the moment, so just 2y. So we'll say this equals, everywhere where x is, we can replace that with 2. So this will turn into 2 squared plus 2y. Plus y squared minus 3 times x is 2, minus 3y plus 3. We can simplify this quite a bit. 2 squared is 4. 2y doesn't really simplify yet. Y squared doesn't either. Squared. 3 times 2 is 6. That's minus 6. Minus 3y plus 3. Then I can combine like terms here. I've only got one quadratic term, so y squared. I've got a couple of linear terms. 2y minus 3y makes negative y. And then as for constant terms, 4 plus 3 is 7, minus 6 is 1. Notice that this is a one-dimensional function. That should make sense because on our left edge, that is a one-dimensional region, so it should be described only by one variable. And we can find the critical point here, just like in Calc 1, just set the derivative equal to 0. This is effectively a new function. It's not exactly the same as the original function, so if I'm going to take a derivative, I'd rather rename the function. So I'm going to call this, say, e1 of y, standing for edge 1. This is our first edge, so edge 1 of y, and it's a function of y, of course. So just like in Calc 1, take a derivative, e1 prime. It's kind of a somewhat overlap of notation. That's a prime and that's a 1 there, so writing it looks the same, but that's okay. So e1 prime of y is 2y minus 1. Same as before, set that equal to 0, solve for y. Looks like we get a nice clean y equals 1/2. And I'll plug that into the table. That is for our first edge, the left edge, y is equal to 1/2. So on the left edge, y is 1/2, there we go. We have to find the x coordinate, and to do that, we just go back to the line itself. This was x equals 2, so naturally, well, x equals 2. We can use the same process for the upper edge, although the algebra will be a bit trickier. The upper edge is described by y equals negative x plus 4, and we can plug that into the function. We'll do the same thing as before, f of x comma, let's see, the edge we're plugging in is y equals negative x plus 4, so we'll replace y with negative x plus 4. And again, there's the function there. So everywhere where y is, we'll replace it with negative x plus 4. So start with, say, x squared plus x times y, but we're saying negative x plus 4 now. And then plus y squared, that's also negative x plus 4, and then squared, minus 3x minus 3y. We'll just put that down here. Minus 3y, once again, is negative x plus 4, and then plus 3. So again, just kind of an algebra simplification problem, although there's a few more details. We got to distribute this time, so we'll say equals x squared. That's going to be negative x squared plus 4x. This one, let's see if we can distribute these. There'll be 4 terms. A couple will combine. You'll get plus x squared plus the product of these two, 2 times the product of these two actually, so that'd be minus 8x. And then plus this square, which is 16. You got that minus 3x there. This one will be a plus 3x, and then minus 12, and then lastly that plus 3. I see a couple things simplifying right off the bat. You've got x squared minus x squared, which cancels out. You've also got a 3x minus 3x. Those cancel out also. After that, I only have one quadratic term, x squared. And then I have, let's see, 2 linear terms. 4x minus 8x makes negative 4x. And then we have 3 constant terms. 16 minus 12 is 4, plus 3 is 7. So once again, we'll rename this. This is our second edge, so I'll call it E2 of, we haven't taken derivative yet, so just E2 of, now this is of x. Same as before, we're looking for a critical point on this edge, so we'll take a derivative. E2 prime of x is, let's see, 2x minus 4. Set that equal to 0. And then move the 4 to the other side, divide by 2, we get x equals 2. So we'll go back to the table. X is 2 on the second edge for our critical points, so that would be the upper edge. X is 2. Once again, we're getting lots of 2's, but that's okay. To find y for this one, we will need to plug that into the corresponding equation. So this was on the upper edge, which is described by y equals negative x plus 4. And we know x now, so we can plug in x equals 2 there. I'll do that down here. So once again, y equals negative x plus 4, but we know x is 2 over here now. And we get a nice clean y is 2. So we'll put that on the table there. On the upper edge, we have a critical point at 2, 2. All right, lastly, the lower edge is described by y equals x minus 2. Same process as before, we'll plug that into the function to get a modified function that exists only on that lower edge. So if that's my function up there, we'll plug in that lower edge, which was x minus 2. This is f of x, comma, we know y is x minus 2 now, so use that instead of y. This now equals, let's see, x squared plus x times, again, replace y with x minus 2, plus y squared, once again, x minus 2 squared, minus 3x minus 3 times y is, again, x minus 2, and then plus 3. Once again, we'll have to distribute everything, so we'll get x squared plus x squared minus 2x, plus, let's see, the square of this is going to be x squared plus 2 times the product of these, which is minus 4x. And then this squared is just 4. minus that 3x there, and then you have minus 3x, looks like plus 6 there. I'll go to another line, plus 6, and then plus 3. Less cancellation this time, just adding like terms. So x squared plus x squared plus x squared makes 3 of them, 3x squared. Then we have linear terms. We've got 4 of them. They're actually all negative, so I can pretend like this is an addition problem. 2 plus 4 is 6. 3 plus 3 is also 6. 6 plus 6 makes 12, and that's all negative, so negative 12x. That covers most of the terms. I just have these 3 constant terms. 4 plus 6 is 10, plus 3 is 13. This is our third edge. Once again, we'll rename that. We'll say edge 3 of x. Take a derivative once again. E3 prime of x is 6x minus 12. Set that equal to 0. Looks like we get the same result actually as before, x equals 2. Kind of coincidentally there, I would expect to get different answers for these. I wouldn't expect them necessarily to be the same thing. Just coincidentally, we get x equals 2 for all of them. All right, we'll plug that into the table. For the third edge, x is 2. So the lower edge, x is 2 once again, for some reason. We need to find the y-coordinate of that critical point. So this is on the lower edge, which is described by y equals x minus 2. So we'll plug in x equals 2 into that. We'll say y equals x, but we know x is 2, minus 2, which is 0. So on the lower edge, we have a critical point at 2, 0. The very last piece we need to test is the interior. This is the only slot left here. So this is where we actually do some Calc 3. We'll set the partial derivatives equal to 0 and solve the resulting system of equations. I'll write down the function again here. We'll say f of xy is x squared plus xy plus y squared minus 3x minus 3y plus 3. And then if we're taking partial derivatives, that's f sub x of xy. This is where we treat x as a variable and treat y as constant, so this becomes 2x. For this one, pretend that's like 5x, for example. The derivative of 5x would be 5 in particular, so the derivative of yx would be y. That is with respect to x. Derivative with respect to x of xy is y. Now, y squared is constant with respect to x, so that one goes away. This one's actually the same rule as this one, it's just the coefficient, minus 3. That one's constant once again, and that one's constant also, so we just have these 3 terms here. The partial derivative with respect to y is going to be pretty similar. The first term goes away, that's constant with respect to y. This one is linear with respect to y, so we get the coefficient, which is x. For this one, we get 2y. Another constant, and then minus 3, and another constant. Just like before, we got to set these equal to 0, and we solve this simultaneous system of 2 equations and 2 unknowns. I'm actually going to move those 3's to the other side. I'll say 2x plus y equals 3, and x plus 2y equals 3 as well. And we have lots of different methods for this. We can use, say, substitution, elimination, perhaps matrices if you've used matrices for solving systems of equations before. This one's not too bad. I'm going to use elimination. Say multiply the second equation by negative 2. You get negative 2x minus 4y equals negative 6. And the reason I picked that is so that you get a 2x and a minus 2x. Those will cancel out if I add them together. So add these, you get 0. Add these ones, you get 3y, or rather negative 3y. And then we get equals negative 3 on the other side. Divide both sides by negative 3, I'll get y equals 1. So that is the y coordinate of my interior critical point. We'll have to plug that back into an equation here to get x, and we can use either one. We'll do, say, the first one here, 2x plus y, but we know y is 1 now, equals 3. Move the 1 over, divide by 2, you get what? Just 1, x equals 1. And if we did the other one, once again, we should get the same result. That's just 2, 3 minus 2 is also 1. So a nice double check there, checking both equations. So we'll put that in the table. For our interior critical point, we got 1, 1. So on the table here, interior, 1, 1. All right, now that we have all of our points, let's graph them to make sure they're all in the region. The first one, 1, 1, is 1 to the right and 1 up. That is right here. That's actually outside the triangle. We want everything to be within this region here. That's on the outside, so we can cross out that first point. We don't need it. Even if we test it, it's not going to matter for our final analysis. The next point, 2, 1/2, is 2 over and a half up, so somewhere below 1 there, somewhere right here. That's on the edge, so we can keep that one. The upper edge critical point, 2, 2, is right here. That's actually the same as that corner. Notice we got a duplicate point. You can always cross out duplicate points. No need to test the same point twice. Next one is at 2, 0, which is 2 over and 0 up, which is another duplicate point. That's actually the same as the lower vertex. So you can cross that out as well. Lastly, we just have the right vertex, which is at 3, 1. The vertices should always be in the region regardless, but it's useful to draw everything just to make sure. All right, so we have, looks like 4 points that we need to test. We'll just need to plug these into the function to get our outputs there. This is a bunch of arithmetic at this point. I did the arithmetic earlier, and you guys can work out the details on your own. You'll find that the outputs here are, we have f of 2 1/2 makes 3/4. F of 2 2 is 3. F of 2 0 is 1, and f of 3 1 is 4. So again, that's just a lot of arithmetic. You guys can work out the details on your own. Those should be the 4 values that we get from there. So that's all we need to find our final answer. We're looking for the minimum and maximum values. The smallest of these is 3/4, and the largest of these is 4. So those are our min and max, and we can present our final answer like we did before. I'll do this down here. So this time I'll say f of xy attains a minimum value of 3/4. That was our lowest value there, 3/4. At, and last time I said x equals, you could say x equals and y equals if you want. I would rather express this as a point. So this would be 2, 1/2. That's the point, the input point that results in an output of 3/4. And then lastly, of course, f of xy attains a maximum value of, we said the largest one was 4, and that occurs at 3, 1. 3, 1. All right, and that's our answer. We can box that. Whoops. There we go. So notice that we actually did end up getting a minimum on an edge. This was 2.5, that's right there, and our other one was on a corner. I've seen plenty of students work these problems like in Calc I, where you set derivatives equal to 0 for the critical points, then test the boundaries, which are just the corners. So the only problem with this method is that it ignores the edges, which are also boundaries. So it doesn't really test all of the boundaries. And clearly we got one of our answers on an edge. So it's really important to test all of the different pieces, all of the boundaries. That's interior, edges, and corners in this case. And you can always start with that if you want to. You can always start with a list of pieces of geometry there. Just keep that in mind. Two-dimensional objects in general are built out of, they have an interior, they have edges, and they have vertices. All right, with that, that's everything I had. Let me know in the comments if you have any questions, if I can clarify anything. Other than that, thanks for watching. Have a great day.